Trees are amazing for the planet. They provide oxygen that most of life depends on. They filter pollution from the sides of roads and cool the air in cities. This can help to save energy on air conditioning and heating by an incredible 30%. A typical oak tree can host 284 species of insect and 324 varieties of lichen, providing food for birds and small mammals. And studies show that trees actually reduce violence in neighborhoods, and they are great to climb. It is really important to protect trees from threats such as tree diseases. That's why we decided to create our project around tree diseases.
Using the language and maths to understand how something works. The more data and the better the model. Once we have our model, we can put it in different things to see how it changes it. Project, we've been looking at how modelling can help us study tree diseases. So we need to monitor which trees are affected, predict what they may infect, and prevent that from happening if possible. And models can help us to study epidemics and help us design surveillance systems. But trees face an uncertain fate with climate change, diseases and pests. So we can look at how the best to spend our money on trees.
To explore the modelling of tree diseases, we've designed a board game that has a network of trees across a specific area. The infection can start at any one tree and then it spreads out from that area. And to introduce the probability of the tree disease spreading from one tree to another, we've used a dice. So for example, if this tree is infected, there is a 4 in 6 chance that any one of these will be infected due to the roll of the dice. And then as there are 3 trees, there's a 1 in 3 chance of it being a specific tree. So that then results in a 4 in 18 or 2 in 9 chance of any specific tree getting infected. If you then move out to a tree like this one, which is a bit further out, the chance then drops again to a 1 in 68 chance of it getting infected. And then there's an even smaller chance of this tree getting infected as it's much farther away, but there's still a chance that it will get infected. Another way we've introduced the scenarios that might happen in real life is with the chance cards. So these chance cards involve things like the spread by water, wind, humans and pests. So for example, if you have a disease tree by a path, infect 2% of trees next to that path. So if you have a disease tree here, for example, you can spread along the path and infect 2 trees next to that path. And that's because there's 100 trees, so 2 trees so 1 tree equals 1% and 2 trees equals 2%. Step in making a model of tree disease is to count and record how many trees there are in a certain area. After that, you have to map where the trees are and network how they're related to each other and how the disease might spread. After that, you have to look at the probability of the disease spreading from one tree to the other and the rate of how that happens. The board game as realistic as possible, we've used data from the Forestry Commission about the spread of diseases in our local area and also across the UK. An example of this is the spread of oak processionary moth that started in the middle of London and spread out from there. Again, another example of this is the spread of cholera from southeast England all the way up to Scotland and down to Cornwall. Game more interesting, we added a counterpart immunity to oppose the disease. But as well as this, we hope to add more diseases, add more strategy and tactics into the game, and also to insert more data. As well as this, we've already improved the model by turning it into a computer program.
We decided to program it in Python 3 and use a function called matplotlib, which helps with visualizing anything that can be mapped or graphed in Python. Like the game, there is one virally infected tree which the virus starts from. The program rolls a random number from 1 to 6, and the virus can move accordingly with that roll and can infect healthy trees from only one virally infected tree. It can be quite hard for you to program a computer with plain numerical codes, because there are a lot of different possibilities that a computer would have to take into account for each relative coordinate. For this reason, we decided to use Pythagoras' circle theorem to work out if a healthy tree was close enough to be infected. We then deleted or appended the relevant data to the end of the list of coordinates for that tree. First of all, we started with a relatively small grid, which was 10 by 10 meters, with about 5 trees in it, but we then moved up to a 20 times 20 meter grid containing 100 trees. This was more like our game. Because of the way we have programmed it, the algorithm can be scaled infinitely, as long as you have the computing power to deal with that number of trees. We've also found that the graphing function didn't work with loads of trees, so we created a graphically free version of the algorithm so it runs at greater speeds without the need to process lots of graphics. However, as the graph gets bigger and more trees are added, so does the time it takes computationally. We ran the program on the algorithm-only version with 10,000 trees on a 1 kilometer grid, and after about 2 hours the program still hadn't finished. The virus too is changeable in how far it spreads, and the chances of it doing so to emulate the spread of a real-world virus such as Chalara. In the future, we would like the program to be able to read viral statistics from a file in order for you to be able to easily change infection rates, like the trees, as their coordinates are read from a file. Then came the testing. We initially started running the program on the scale of 1 month, but soon changed it to years instead, as the program became far more realistic if we did this.
Our program could be developed further so that we could predict the progress of tree diseases across the UK. This could help us to decide which new trees to plant and in what areas, or whether a species of tree is likely to be entirely wiped out. This would enable scientists to prioritise treatments or development of new varieties of tree.